Hi, in this video, we want to take a look at using variable transformations to improve our linear model. All right, so we're in the situation where our model doesn't exactly fit the hypothesis, the assumptions needed for hypothesis testing. And we want to do something about it so that we can go ahead and proceed the way we would like to. All right, so there's certain assumptions we need to be able to do regression. To be able to do regression, all I need is finite expected values. I'm out in public, so I'm gonna maybe have to pause for noise every once in a while. So we need expected values to be finite, expected variances to be finite. That's all I need to be able to just build a regression model. Now, the reason for that is because of really just because of geometry. The line of best fit is a geometric mathematical object. Now, what follows after that, everything that we do after that in statistics, that's really like a probability and statistics aspect of what's going on. So the assumptions for a regression model is very, very little, very, very light. You know, virtually all situations that we're collecting data, we're gonna have finite expected value, finite variances. That's really not a high bar to get over. Now, if I want to be able to do hypothesis testing, for example, I want hypothesis testing or confidence intervals on my coefficients. I want to do hypothesis testing from that F-test. If I want to do, other aspects, anytime that I need anytime I'm going to want to use a p-value, which has an assumed probability distribution, I need to have other assumptions. The one that we're going to be concerned about today is going to be constant variances of residuals. Now, when I say constant variance of residuals, that means with respect to the predictor variables. So if I have a predictor variable and I see that I don't have a constant variance of my residuals, then I need to pump the brakes on hypothesis testing. Now, the model can still work, that is the line of best fit, but I don't get all of the other nice features I get from probability and statistics. I can only use a geometry to get the line of best fit. All right, so the example we're going to look at today is taken from the textbook website. Now, when I have issues, one of my options is to transform my data. So there's two major ones. Okay, so any mathematical function, any function from college algebra, you remember when I have one input, I get one output, that's a function. So for us, any function could be potentially used, but there's some that statisticians before us have identified as being more useful than others. The two most common ones are going to be the square root transform and the log transform. We're going to frequently use the square root transform when I have count data. And I'm going to frequently use log transform when I have skew right data. Skew right data will come up a lot when I'm dealing with money, financial data. So just be ready for that. So if I see money and you see issues with your model, just immediately knee-jerk reflex, think log transform. Now, when I say log, we can use either natural log or we could use base 10. We could use any base possible. Use what would be most accepted by your audience. Square root transform, if I have count and data, look for the count, look for square roots to be the way to go. The reason for that is because of features of the Poisson distribution. All right, so let's get into our code. So first thing I do is I go ahead and I load my data. Well, I actually set the digits down to 2. I load the data and I take a look at it. So I can see in my data, I've got number of crews and the number of rooms cleaned. Okay, so here, let's say that I'm running a hotel, something like that, and I've got a cleaning crew. And I need to know, like, how many crews do I need to be very efficient? Like, for the size of the job, how many people do I need to cover that? I want to have, exactly the right number of people, the right number of crews, because if I have too many, I'm losing money on payroll. If I have too few, then I'm not meeting the demands of the employer, of the clients. So I want to be in the narrow spot. It's a Goldilocks problem. Not too many, not too few. It needs to be just right. All right, and we can see that if we scroll down, we have what? Let's see, 53 observations. All right, it's a small data set. Now, so what I'm going to do at this point, I'm going to go ahead and I'm going to color my data points. Whenever I plot, I'm going to color the data points by the target variable. That is a good way to show features and help me understand and spot things that's going on. In this example, it's not going to help us, but it's still good practice, so I include it. All right, so let's go ahead and start out. I'm going to build the vanilla model. What's going to happen is I'm going to run diagnostics, and I'm going to go, hey, there's something wrong with this. I know this because I've already built, you know, the code and did everything. And then I'm going to be like, hey, how can I fix this? How do I fix this problem? So I go ahead and I just build my regular model. Now I'm going to use the summary function to take a look at the output real quick. All right, so these residuals are kind of big considering the size of the numbers I've got, but you know, sometimes it just works out that way. I can see that definitely statistically significant within machine accuracy on the cruise coefficient. The F statistic is within machine accuracy of 0. You know, that's pretty good. R squared of 0.86 and 0.85 for adjusted R squared. So those are close together. So I'm not worried about overfitting. And 0.86 is pretty good to see. I can tell you at work, I would just be absolutely ecstatic if I could get 0.86 on a lot of the data I work with. All right, so let's go ahead and plot our vanilla model. So remember, the most important diagnostic I can do for a linear regression model is a standard scatter plot. Now, something I'm going to do that's a little bit different on this one is I'm going to do a 95% prediction interval on our plots. All right, under the assumptions of linear regression, if the model is correct, I have for each given X value, I have an interval where 95% of my observations would land if I kept on collecting data, and that is our prediction interval. So this is like 95% of the observations for the given X will be within that certain width. Now, this does not tell me about the expected value. So this is not confidence interval. This is a prediction interval. All right, well, to be able to do this, I'm going to need to use the predict function, and I'm going to go ahead and build a score data set. Remember, the training data is the data I build the model on. The score data is the data that I make predictions on. So the data that I haven't seen yet, or where the room number or the number of rooms is not known. And I go ahead and this part is the same as we've been doing before. This code is being repeated because of the fact that I'm doing this in R Markdown. If I was doing this at work, I would not be repeating this part of the code. All right, so here is the plot, and I don't see any major problems, but you'll notice that these points are kind of tied together. It's a little bit less tight, a little bit less tight, and these are pretty spread out. So what we're going to see as we progress through this example, we're going to see that these points are getting more dispersed as we go from left to right. Well, if they're getting more dispersed as we go from left to right, then I have non-constant variance, and that is a violation of the assumption needed for hypothesis testing. All right, so I'm going to go ahead. Here's my scoring data. So I'm just taking the number of crews from 2 to 16. That was the smallest value is 2, the largest value was 16 in the original data set. So I'm staying within the range that I have in the original data. And then I'm using the predict function. So we're predicting on our linear model. Our new data is that scoring data. And I'm getting a prediction interval. And it's a 95% prediction interval. Now, something about R. R has a lot of different structures for storing data. And this is a maddening aspect of R. This is Python is actually, I consider Python to be even worse on this point, but R is definitely frustrating. SAS has got this down. SAS has got it going well. So to be able to work with this the way I want to, I need to say that it's a data frame, and I'm going to need that for when I do my plotting in a moment. Okay, so I just pass it into a data frame. It converts the format. Everything's good. Easy. It's not hard if you know how, but if you don't know about that, it's absolutely maddening. All right, so here I can get the fit. Here is the lower bound on that prediction interval and the upper. Now, when I look here, when I get negative values, I know negative values don't make sense. So in reality, when I look at it, I would go 0, 0, 0, you know. And these values are going 2 to 16. So the row numbers are 1 off from what I really want. I should have set the row numbers equal to 2 to 16. Make it a little bit easier to interpret. And here we're plotting. Now, at this point, I'm using the lines function to put the lower bound and the upper bound of the prediction intervals onto here. All right, well, you can see that they're parallel. And you can notice that everything in here on the left is like really tight within the prediction intervals. But once I get to the right, almost all of the points that are popping out are on the right-hand side. So that's kind of alerting me to that we have non-constant variance in this data set. All right, so let's go ahead and do our diagnostics. Now, what I call like vanilla modeling is anytime I'm just doing regular linear regression. So anytime you hear me just say vanilla, that means I'm doing a linear regression model. I'm not doing anything exotic and anything that exciting. All right, so let's go ahead and plot the points. I went ahead and did it manually for this one, just because this is so important. And I'm taking the standardized residuals. So I interpret this the same way I would the normal distribution. And look at this. My maximum and minimum are on the right, like to the right of 9 is where I got the most spread, and to the left of 9 is where I have the least spread. And things are kind of tight over here. So I'm getting concerned, getting worried. This is leading me to be more confident that we probably have non-constant variance. Okay, well, what I'm going to do, I'm going to go ahead and take a look at the square root of the absolute value of the standardized residuals. A lot of times the square root of the absolute value of the residuals is easier to interpret. All right, so residuals are positive and negative. Remember, residuals always add up to 0. So approximately half are negative, half are positive. Well, if I want to take a square root, I can't have any negatives, so I take the absolute value and then I square root them. A lot of times it's easier to interpret our residuals when we look at them this way. And I go ahead and I plot. And look at this. I can see that the magnitude of the residuals is increasing as the number of crews increases. So the residuals, the absolute square root, the square root of the absolute value of the residuals is increasing as the number of crews increases. All right, so this is not how I want it to be. I don't want to see a pattern anytime I look at residuals. If I look at residuals, I don't want to see a pattern. And here, this is strong enough of a pattern that I'm like, okay, this is not the model to use. Pump the brakes, do something about this. All right, so what I'm going to do, I'm going to go ahead and go through the 6 standard diagnostic plots. And I'm seeing the same thing. I can see that for the normal QQ plot, this is a little bit higher than I would like, a little bit lower. These 2 points kind of popping out at me, these points. So got some concerns on that front also. You can see the standardized residuals, square root again, definitely a problem. Cook's distance. Now remember, there will always be like some points that are getting flagged. So what jumps out at me is that these are lighter, like, you know, the ones with the biggest Cook's distance are lighter values. Remember that I colored it by my target variable, which visually on the scatter plot is correlated with cruise. So overall, that's leading me to believe that as cruise get bigger, the Cook distance might be also getting bigger. So, you know, there, some things are kind of like, whoa, 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 we need to do something about this. Here we've got Cook distance by leverage. All right, so remember, leverage only considers the predictor variables. When we do simple linear regression, or actually linear regression always is going to have the predictor variables are the only ones that enter into leverage. Well, remember that the far points on the right were the most, you know, that's the largest predictor variable values, and, you know, they're getting flagged. So there's some stuff going on. All right, so what I'm going to do, I'm going to go ahead and use the text function to plot which points on the scatter plot are the ones that are getting flagged. So if I was doing this in real life at this point, I would be like, okay, something's going on. I'm not really trusting it. Let's go ahead and check to see that. Let's look at the flagged data points to see if there's a problem. That's my first go-to, because remember, if I have poor quality data, anything that's less than optimal is going to propagate through. Any errors, any mistakes, any poor decisions propagates through the rest of the process. So data, which is earlier than modeling, data is more important. I want to check my data at this point. So I go ahead and I flag it. I can see 4, 5, 46, and 31 are the ones that were flagged. Well, 3 out of 4 of those points are on the far right. They're high leverage values. And I can also see that they're the most spread out from the line. So yeah, I need to do something. Overall, I'm not really that concerned about the data being wrong. I don't feel like I need to filter out, but you know, there's enough stuff going on that I think what's going on is that the structure of the model is not sufficient. So let's look at the variances of our residuals with respect to the number of cruise. Okay, so what I need to do for each value of cruise, I'm going to take the standard deviation of our target variable for each value of cruise. So when I have 2 cruise, take all those data points, take the standard deviation of the target variable. When I have 4 cruise, take all those data points, take the standard deviation of the target variable. I'm going to repeat this all the way through. So to do this, I'm going to use the tapply function. So what this is going to do, tapply is going to take our target variable, I set that equal to x. It's going to group the data by the index, which is our predictor variable, and I'm going to take standard deviation of each of those subgroups. All right, let's take a look at what we get. Let's take a look at the bar plot. All right, the bar plot is pretty clearly increasing as we go from left to right. All right, so I know I do not have constant variance with respect to the predictor variable. So I need to do something about this. The 2 standard ways to do this is going to be a square root transform or a log transform. Now, what you do in real life is you start playing around on, and just, you transform a variable, look at the model, transform another variable, look at the model, transform, and you play around with it. Now, when I see count data, square root transform is frequently the one I want to use. If I see highly skew right data, log transform is the one that I want to use. Now, natural log or base 10, I personally use natural log, but I would use base 10 if the audience that I'm making the model for would accept that better. Now here, I went ahead and made a regression model with crew numbers and standard deviation, and yeah, we got a problem. Houston, we have a problem. So what we're going to do is we're going to go through and we're going to transform, after playing around with it, stuff that's not included in the video, not included in the example, try different transformations and then run with one that looks best. So here, the author and I both agree on this, that the best transformations are both on the target variable and on the predictor variable. Now, why is it that the square root transform works? It works out that if you go through the theoretical statistics, your mathematical statistics course, STA 4321, if you take a Poisson distributed random variable and take the square root, you will have approximately constant variance in the way that we want. Now, it's only going to be approximately a constant variance, but it will be close enough for us to go ahead and accept it. That, remember that there's always like errors in our measurement anyway. Nothing's ever perfect. If I improve the model, I'm happy. I want the best model that the data will support. So what I'm going to do, now this is where I step away significantly from the author's version of the example. I go ahead and I run square root inside the formula. The author went ahead and ran square roots on the data set. Now, there's advantages and disadvantages on that. Like here, I knew the square root was going to work out, so I just put it into the formula. This means that when I run my prediction, when I run functions, R will go ahead and automatically do that for me. That's a great bonus. A disadvantage of that is if I have like big data and I have to like perform transformations and I'm exploring a lot, it might take a long time to be able to run things. So if I end up if I have to repeatedly do square roots as I try different models, then that can take a long time. I would want to take a square root, store that data, and use that data that way. But for this problem, the slicker way is to put it inside the model. Since it's inside the model, I can rest easy peasy and let R do all the work when I do my predictions and my confidence intervals and stuff like that. I just have to kick back, relax, and enjoy it. All right, so now let's take a look at our residuals. Well, all right, so first of all, they're much smaller than they were before. Now remember, this is on the square root scale. So when I interpret this, I need to take the square of it, but it's still a lot smaller than we had before. So I'm a lot happier with this model than what I had. Here, the coefficient is statistically significant. F statistic is statistically significant. And I can see that both R squares improve slightly. It's almost 0.9. If you see 0.9 on a regression model for R squared, be happy. You're not going to see a lot of those in real life data. So if you see 0.9, yeah, that's some good stuff. Anything involving human beings is like 0.9 is going to be very rare. You'll see 0.9 like physics experiments and stuff like that. All right, so what I want to do now is I want to go ahead and get like that prediction interval again to see, like, to visually indicate how much of an improvement this is. And so what I need to do, remember, the model was working up on the square root scale of the target variable. So when I make a prediction, I have to square it to undo the square root. And so that converts it to the scale I actually want it on. So something that's very important in my code, and it's very subtle, it's very tiny. You see that caret 2? That is telling R to square it. It's hip to be square. So now let's go ahead and plot this. Everything's pretty much the same as I did before, except now, one thing that I'm doing that's different is I'm coloring it blue, and I'm using a different line type when I plot my square root models. So remember, if I want visualizations to pop and be distinct and be easy to interpret, I want to put as much features onto important variables as possible. So on my model lines, line type and color are indicating which model it's going with. I could have also done line thickness if I thought that would have been appropriate. Thickness can also imply other things, so I didn't choose to do that. So let's go ahead and take a look at the plot. All right, so now when I look at the blue, you can see that the blue is tighter on the left, and then it does a much better job fitting the data. It goes, my prediction intervals fits very nicely. Now, the dashed blue line is not a straight line. It's there's a curvature to it. If I algebraically went through, it's going to be the squaring of coefficient times square root plus coefficients, plus a constant. And that's not going to be a straight line. It's going to be close visually, but if I was to go, if I insert like really wide range of values and ran prediction, I would be able to see that it's not a straight line. So we can see that it fits the model much better, but I'm feeling good. This is a good model. All right, let's go ahead and do the diagnostic plots. So I've got the standardized residuals. I don't see a pattern right now. Now the color is increasing as we go from left to right, but that's okay because cruise is along the x-axis. And so if I have a good model, the y variable should increase along with the predictor variable, which is exactly what we're seeing with the color. So it gives me another indication that things are going well. Now let's go ahead and run through the 6 standard plots. Notice that I am coloring the points and I'm using all 6. I have to specify which equals 1 through 6. I have to specify which equals 1 through 6 if I want to get all 6 of them. If I only want a few,